2018. Bhattacharya has been a member of visiting faculty at Stanford in the year 2005 and Johns Hopkins in 2012. Bhattacharya works in probabilistic mechanics and explores how random atomic scale structural defects and fluctuations affect material properties at the microscale and how that randomness, coupled with uncertainties in the environment, affect the performance and safety of structural components and systems. He works on probability-based design and reliability analysis of civil infrastructural systems in structures such as nuclear power plants, ships and offshore structures, buildings and bridges. He was an associate editor of the ASCE Journal of Bridge Engineering during 2010 to 2018. He has held the position of chairman, civil construction and maintenance, and the dean of international relations at IIT Kharagpur. He was elected fellow of the Indian National Academy of Engineering in 2016 and a fellow of American Society of Civil Engineers in 2018. He has several publications to his credit, and I request all of you to visit the Google Scholar website to know more about his publications. And he is well known in the field of reliability analysis. And now I think at characterizing the material properties, taking into account the defects at nano level, micro level. I request now Professor Baidurya Bhattacharya to deliver the keynote address on deriving target reliabilities from socio-economic considerations, a well-meaning but impractical approach to design. I request Professor Bhattacharya to deliver the lecture,
please. Thank you very much, Dr. Balaji Rao. You have always been very kind to me, and most of the adjectives you mentioned I don't deserve. But let's start with the topic. So it's quite a long title. It is, and obviously we mean structural design target reliabilities. And I want to come to the this approach of developing target reliabilities for design from socioeconomic considerations, but that will happen at the very end of this talk because I have to set the context. And then leave you with a question, is that whether that is at all a feasible approach or not. So let me start with the first part of my presentation. There will be actually 4 main parts, and I want to kind of walk you through the history of this subject as I come to the main topic of this talk of a socioeconomic approach to developing target reliabilities. So part 1, just a few slides on what is reliability-based design. This should be quite obvious to all of you, but for some students, just a little bit of recap. So let us say that we have a structural system, a system whose mechanics we understand. And this is the simplest possible configuration that you can imagine. It's a cable suspended from the ceiling. So we know the purpose, the environment, the expected service life, and how it behaves to external inputs. And what we want to do is to assess this system. We know its system properties. We know the inputs, the response, the input-output model, which is very simple here, as you see on the left part of your screen. On a more realistic structure, we would have a finite element model. What's important is there is a system capacity, which we know precisely, and that is that comes out of our understanding of the application, the purpose of what this is. So here, let us say the capacity is defined in terms of a displacement. So we should be able to define failure in terms of response exceeds capacity, which in this case is what you see on the left part of your screen. PL over AE is greater than delta max, which is the capacity of my system. Now, there are many issues, time dependence and etc., which we don't need to touch for this particular. The capacity can be two-sided, not one-sided. But the important point to note here is that there are uncertainties. There are uncertainties in the input to the system. There are uncertainties in the properties of the system. The model, the input-output model itself can be idealized, so there are uncertainties there. And other issues like missed or unknown modes of failure, etc., etc. So what happens is failure, which is the response exceeding the capacity or the system behaving in a manner that is not acceptable to us, because of these uncertainties, has a non-zero probability of occurrence. So that is where we come in. On the bottom left of your screen, you see the failure probability expressed in terms of the so-called basic variables. Now, if we understand the mechanics and if we understand the randomness involved, we have the ability to compute the probability of failure. And then, obviously, we have to come to a decision. So that is the crux of the matter, that is it acceptably low? If not, then we have to redesign. And is the solution economical? And then the question is, can I standardize this process? Every time I don't want to do this, this is too time consuming. So can I come up with an approach which would take care of all of this in the background? The uncertainty is all the finer details. So basically, can I have a design guide? So these 2 points, that what is acceptable as a failure probability, and can I standardize this process, basically gives rise to this new crop of reliability-based design codes, which we have been witnessing for about 40 years already. So starting in the 1970s and maturing through the 80s and 90s, almost all design codes in structural engineering all over the world are now reliability-based. So the question is that what reliability do they impose or they promote or ensure, and how do we get them? So that is the point of target reliability. Now, we could express the activity or the process of design, structural design or any design, as an optimization process, because we know it's an iterative process. We could also cast this as an optimization, which will be useful in the later part of this talk. So let us just go through this. An engineered system is expected to satisfy certain performance requirements while being economical and safe. So that's a very general statement. And the emphasis, whether on performance or on safety, depends on who you're talking to. So it depends on the stakeholder. And in general, it's a multi-objective optimization. So it's a very difficult problem to solve. But if we can strip it down to its absolute essential, then one approach could be to minimize the cost, the total cost, subjected to performances being met, theta being the performances, and safety margins being acceptable. So M is safety margin, theta is performance, and the stars, the asterisks, are the acceptable values. You can obviously have this two-sided, a lower bound and upper bound, but here we have lower bounds. Now, this is not the only way that you could do this. You could maximize, look at the dual problem, you can maximize performance, subject to the constraints and safety. You can bring in benefit, so benefit minus cost, the net benefit. You could maximize the benefit instead. So these are all equivalent approaches to design. You could also maximize safety, but obviously, you know, safety is typically a constraint. If safety was an objective, then it would be a different system, but that we would be interested in. But yeah, in general, that's also an acceptable approach. Now, the question is, we need to define the costs and benefits properly, what to include, what sort of failure costs need to be taken into account. Is it the publics, it is the owners, or is it some other stakeholders? And finally, the question that we started with, what about the uncertainties? The moment you bring in uncertainties, then the presentation of this optimization problem has to change. And what becomes different? First of all, the objective function, the constraints, even the decision variable. So one very common way is to minimize, instead of the total cost, the total expected cost. And likewise, you would expect that the constraints, even if they're not satisfied, they should be satisfied most of the time, which is acceptable to you. So the performance constraint should be satisfied with at least a probability Pi. The safety constraint should be satisfied at least with the probability R, which is the reliability that we have been talking about. So the question is, how do we get this? And there are issues like you could do it for systems, you could do it for components, you could do it for various types of limit states. So each of these M's, Mi greater than Mi star, they basically comes from some performance requirements. So these could be given with the help of mechanics in terms of limit state equations. So you could have life safety limit state, you could have on the other extreme functionality limit states, which could be reversible and irreversible. So you could have a set of limit states for a structural system or a component. What we are interested in here is in life safety. So from this point on, we are going to talk only about life safety and how to set these target reliabilities. Now, so these are the questions that how safe is safe enough? So at the moment you're talking about life safety, how much risk to life and property and environment is acceptable? What failure consequences need to be taken into account, because that basically determines how safe you want it to be. Equivalently, how much loss is acceptable, how to handle partial failures. And if not safe enough, you have to redesign, or so how much money to spend. And after setting the target reliability, although it's not part of this talk, but in general, it's very important to communicate the risk properly with the owners and the stakeholders. And more finer details like there are differences between the actual risk and the patient. The tolerable risk might change with time, and that's something you observe in different societies. It also may depend on the sense of control, whether it's voluntary risk or involuntary risk, and all sorts of things. But when we set target reliabilities, especially in life safety, these issues have to be kept in mind. Now, before we discuss all the different ways and the history, let's make some very important observations. So these are some of the facts that structural failure are rare events. So also large-scale testing of nominally identical buildings, bridges, ships that we typically deal with to failure is not possible, which is different from what is done in other disciplines in reliability. Those that have nominally identical components, electronic components, electrical components, that we do not have the benefit of in structural engineering. We can test structural components to failure. You might be wondering, we do it all the time in our structures labs, but what that gives you is basically an estimate, a random estimate, a probabilistic estimate of the strength of these members and modeling uncertainties, if you like, but not the actuarial, not the frequentist failure data. That is not obtained from labs in our structures labs. So what we can do using mechanics is compute the failure probabilities. But the central question is, when we try to set the target reliabilities, is that can the computed probability of failure be compared with PF based on failure data? We can get some failure data from the field, but can we compare them with our computations? Is our physics so accurate? Do you understand failure so well? Is our knowledge of randomness, all the randomness is involved, do we have complete information about them? Because finally, we are doing some probabilistic computations. And finally, even if you are able to compare that with the failure data, these are rare events. So are the data so comprehensive? So these comparisons become very touchy issues. So when the very first generation of codes that we started seeing, they tried to avoid some of these questions, and through the process of what we now call as calibration. So let's go through some statements of one of the earliest researchers, the pioneer in our field, Professor A.M. Freudenthal. So if we look at some of his statements from his 1956 paper, these are some, clearly the seeds were sown even that far back. So if you look at some of the statements that we need numerical values for probabilities of failure, of avoiding failure and loss of functionality, the idea of cost came in. So the cost minimization, the expected cost, that was also there. Now also, if life safety is involved, the author was very cautious about the acceptable failure probability, and he said that should be practically zero. We understand that it's not possible now, so we have accepted to have very low failure probabilities that are acceptable to all stakeholders. But the idea of life safety and a good reliability for that is also very old. Now, Professor Freudenthal also admitted that it is not possible to do this for buildings from first principles. So until that was possible, comparison with other similar systems is what he recommended. So this is actually what ends up being calibration. So we now see that we have calibration-based methods to setting target reliabilities and consequence-based methods, which would be fatality and economic losses. And very recently, we are seeing some movements towards optimization-based methods, and that's what is what I want to leave you with some questions. So let's go through calibration. So that's the earliest codes basically looked at calibration. So this is the general statement of structured reliability. We have a limit state. We have a set of basic variables X. And when we say failure probability, we basically find the probability content over the failed region in the basic variable space. So if we have just two random variables, capacity and demand, then obviously it's a linear limit state, but in general it's not. And the very famous term that we use, beta reliability index, it's related to the failure probability through the equation that you see on the right of your screen. Now, what do we do in calibration? So we select some successful items of the same type that we want to find target reliabilities for or set target reliabilities for. They must have had a successful history. We must be able to evaluate them through the proper mechanics. We should have enough data of the uncertainties involved. And then for similar items, we can set the reliability for the new items based on what we have observed for these items with successful past histories. So that is what is done in calibration. So we basically calibrate reliability to past successful performance. And that's one good way of avoiding some of the questions that we just asked in the previous slide. Now, pros and cons. Good when the pace of innovation is slow, but if there is some suboptimal design, calibration can obviously perpetuate that. So we have seen how this can be done in the earliest literature from the 70s and 80s. So here are some examples, some outputs from some of these classical papers. So you see that this reliability index, even if there are past successful performance, is not uniform. it varies from material to material, it varies from different load combinations and load ratios. So the question then was that what do we set it to? And if everything is brought together, this is one of the early summaries. So you see that the target reliability for gravity load, the index is 3, for gravity plus wind is 2.5, for gravity plus earthquake it's 1.75, and so on. And you can see then those in American codes, in Canadian codes, in European codes, etc., etc. So now, if you look at bridge code, the Aster bridge code, you can see some similar values of beta. Now, the question is that why is there so much variability? Are they intentional, or are they just happenstances that need to be corrected? If I have collapse as the consequence of failure, then whether it's gravity or gravity plus wind or gravity plus earthquake, why would they have so much difference? And even if beta of 3 and 2.5 might look quite close, if you convert that into failure probability, as you see on the left part of your screen, on the bottom part of your screen, they can actually have 5, 10, or 20-fold difference in failure probabilities. So that's not small. So this question actually started bothering investigators, and starting in the 1980s and 90s, we see some steps in moving towards away from calibration towards consequence. So if the consequence is the same, the target reliability should be the same. So that was the idea. Let me give you some brief summary of that. One of the earliest examples was the Canadian code S471 for offshore structures. And here we see some very far-reaching thoughts, is that they defined 3 safety classes, safety class 1 and 2 to do with life safety, and corresponding to those, annual target failure probabilities were set. So safety class 1 had great risk to life and environment, class 2 had smaller risk, and the target failure probabilities were chosen accordingly. The difference was that now what CSA said was that the load factors should be calibrated to these targets, not to existing structures, but these new consequence class based target failure probabilities. What they avoided was that that any optimization based on costs is something that the owner can take up if it helps him or her in cost reduction, but these target failure probabilities are absolutely sacrosanct. And being a national standard, their interest was public health and public safety. So it's very much understandable. And safety class 1 was the default case. The owner had to actively show that safety class 2 can also be applied. So we also see, along with this consequence based approach to design, an increased participation of the owner and the designer. The designer was no longer a passive person just doing the computations. He or she also has to take decisions based on the understanding of the system. So now, just the same year, we see some very similar thoughts coming out of Norway across the Atlantic. And what they did, what DNV did, in addition to what we have seen in that Canadian standard, is that not only the consequence was brought into the picture, but another degree of freedom, which is the type of failure, the nature of warning. Is the structure redundant, or is there sufficient warning available or not? And you could compare these with the values that the Canadian standard proposed. And we see that there is a 1,000-fold difference between the lowest value and the highest value in terms of the acceptable target failure probability. So starting in the early 90s, consequence became more and more center stage away from calibration. We see the same thoughts in EN 1990, the Eurocodes, which came out in 2002. So we see 3 consequence classes, and again, clearly consequence given in terms of loss of human life or other consequences. Based on that, the target reliabilities were proposed. So based on these consequence classes, there were reliability classes, and the beta values were specified. We see similar sentiments in ISO's 1998 publication on general principles on reliability. This was changed in 2015, and that's going to be one of the last points I make. The change was made by ISO from life safety to economic optimization. Now, AC7 came out around the same time. They also had very similar thoughts. So we see the worldwide, these thoughts are kind of coming together. So there are risk categories 1, 2, 3, and 4, great risk to life versus small risk to life. So these are defined. We could take time to read through them. But the point is that these can actually be compared to the Eurocode's consequence classes. So risk category 1 and 2 from AC is something like CC1 from Eurocodes. Between 3 and 4, it's CC2, and between mostly 4 is CC3 from Eurocode. So there is some sort of parity. And then based on these, AC was able to provide structural, all these target reliabilities for structural design. So you see these vary from 3.7 all the way up to 5.2. We are talking about reliability indexes. So while this was going on, there was also a parallel thought, is if life safety is really what we are concerned about, can we not bring in actual probabilities of loss of life or fatalities and bring in and tie these target reliabilities for our buildings or for our structures to these explicit probabilities of loss of life? This would make things very clear. This would make the risks very clear. And also, you would not have to bring in monetary values of human life because it's always a very touchy subject. So we could bring in a risk approach, and risk, as you know, is the probability of an undesirable event times the consequence of that. So if we can bring in, if we can understand the risk of an activity and we know what a tolerable risk is, we understand the consequence, so we could find out the target probability P from that. And if that's given in terms of lives lost, so that would clearly give us a target reliability to approach. So these are some of the questions that we need to ask. What risk to life is acceptable? Is one life at risk or multiple lives at risk? Was there a choice? Are we talking about construction workers whose life is, whose profession is actually very risky, but can we argue that it was voluntarily chosen versus a person who is in the building without that choice? So choice matters. Do we have to bring in value of human life? And can we avoid doing that? So individual risks to life, there are several standards that we find over the years, over the last 40 or 50 years, that have come to be values that are clearly unacceptable, values that are kind of acceptable, and values that people are happy with in terms of, or okay with, not too much worried in terms of probability of loss of life. And these are some of the numbers. So all causes, an individual's probability of fatality in a year is roughly 0.008. And then if you keep looking at different subgroups of this, different activities, you look at young people, you look at traffic deaths, you look at traffic deaths in different countries, You look at gun violence, you look at completely uncontrollable natural hazards like lightning strikes, and construction workers or some hazardous activities in the industry. So these vary over 4 orders of magnitude. So the question is that where should we put the acceptable bar? Now, one of the earliest works that dealt with this had to do with aviation, and it was concluded that something like 10 to the power minus 3 per year is too high. It's clearly unacceptable to everyone in every situation. 10 to the minus 4 per year are kind of acceptable, but not happily. 10 to the minus 5 per year, people are becoming comfortable, but they are not oblivious to the risk. And 10 to the minus 6 is something like an act of God, and there is nothing to be done. So what the community did was coming up with different, we see in the different countries around the world, the acceptable limits of risk to the public coming close to 10 to the minus 5 to 10 to the minus 6 per year. So these are some of the very common standards from all over the world that we see. So if we take this about 10 to the minus 5 or 10 to the minus 6 per year as a target, then where do buildings stand? So in general, we see that building failure is of the order of this. And what happens now is if multiple failures are involved, if multiple fatalities are involved, all the numbers that we saw so far are in terms of one individual life. So this also has been discussed, has been researched for almost 50 years now. One of the earliest examples came from the construction industry in the UK. So their approach was it's proportional, inversely proportional to the number of lives at risk. So more number of lives, the higher should be the target reliability, the less should be the acceptable probability of failure. And it also depends on some factors like choice, available warning, and so on. So we see some of these values for KS, which brings in those factors of choice. We see some similar thing from Professor Dave Allen's work from Canada. He also included a warning factor. We have seen that sort of thing before. His approach was square root of n in the denominator. So it became less sensitive to number of lives lost in his model. We have seen something similar in the 1998 revision of ISO 2394. It's that it's square of n in the denominator. So more number of lost lives in one event has to be avoided in that proportion. So it's square. So there is still a move in terms of bringing in these fatality considerations and setting target reliabilities explicitly based on that. So this is kind of putting everything together. We have the ability. But what we see is that another movement started about 20 years back with the publication of the Model Probability Code by JCSS, the Joint Committee on Structural Safety out of Europe, which has actually later been adopted by ISO 2394 in 2015, which has taken the very bold step of putting in an indirect manner a monetary value of human life. So that I call postmodern, and let's see what the consequences of that has been. So let's go back to the optimization approach that we talked about. So the traditional way has been to minimize the total expected cost subjected to constraints which are now probabilistic in nature. The last constraint involving M is the reliability constraint that we are all familiar with. Now, you could do something similar for, instead of total cost, net benefit, B minus C, but it looks the same. If you like to bring in uncertainties, so you maximize the expected net benefit subject to these probabilistic constraints. This is all something we have seen early on, but starting with JCSS, as I said, in the late 90s, early 2000s, we see a very different approach. And that's what you see on the right side of your screen. The maximization, the objective is still the same, but those constraints on reliability are gone. Now it is all cost-based, and the constraints are very interesting. So let's take a minute to go through the constraints. So if you want to make something safer, you have to invest, you have to pay for it. So that is obvious. So suppose you have an intervention or a measure, one of the decision variables X, you increase that, say the central factor of safety, by a quantity delta X, and that would cost you some money. So delta CI, the investment cost, goes up. So that has to be at least, so that marginal cost has to be at least as much as what the value of the resource you're saving in return. So that is the idea. It has various names, but commonly that goes by society's willingness to pay, or the incremental cost to avoid a fatality. So on the right-hand side of that inequality, in that constraint, you have the delta expected value of S. So the expected number of lives or expected resources that you can save by that intervention, and that should be multiplied by the value that you hold for that particular object. So if it's a human life, you can, in a very indirect manner, you can say that, yeah, this is what society is willing to pay to save one human life. So the cost of the intervention should be at least that much. But if you do an optimization, typically that constraint is satisfied just exactly. So you get an equality in the constraint. What does that lead to? So if you see some of the recent works, this is JCSS's target reliabilities, and you can compare that with the old ISO 1998 based on their value of human life that was indirectly assumed in terms of, I'll come to that, life quality index. The numbers are more or less the same. If you compare the red with the black, you get the same, roughly the same values. The red ones are the previous standards from the ISO 1998, which came from, not from monetary considerations, but from risk and consequence considerations. But even though in the context of Europe, these numbers are more or less the same, the important thing to note is that the consequence that JCSS took to is not in terms of lives, but costs, the relative cost, the ratio of construction cost per failure cost over construction cost. So the number of lives lost, or what the value of life is, was completely avoided, and everything became very monetary oriented. This approach was taken up by the next revision of ISO when they brought out the 2394 standard in 2015. And the basis of that was this life quality index. As I said, that saving life costs money. So how much money are you willing to spend to save a life? That would sound reasonable, but if the approach is not done properly, then we come with some very absurd numbers, which is what I will end my talk with. So this is the life quality index given in terms of GDP and life expectancy. So you can question this because GDP and life expectancy are very related measures. So why have another index in terms of two very dependent parameters is a question you can definitely ask. So now, what is the approach? That, as I said, the incremental cost of that investment has to be at least what society is willing to pay. So that GD is society's willingness to pay times the expected number of lives that you can save by that measure. And there are various assumptions and computations that go on in the background, but with all these quantities that you should consider according to ISO 2394 2015, the construction cost, the obsolescence cost, the central safety factor, which is the decision variable that they have chosen, the number of fatalities, the willingness to pay that I mentioned, the cost, the investment cost, the discount rate, and so on. If you apply that to a building or to a group of buildings in Switzerland, you come up with the failure probabilities, the annual acceptable failure probabilities, which are there within that green oval that you see. They are basically the same as what we have seen in Eurocodes, in ASCE 7, or even earlier codes that came out of Canada or Norway or United States, etc., etc. These numbers don't really change because you can imagine that even if you change something, you need to make sure that it's acceptable to your target audience. So, but if you apply these to a building in India, you get something very absurd. And so if you bring in this SWTP, Society's Willingness to Pay to Save a Life, and according to their computations, according to ISO computations, what India is willing to save in terms of saving a life, is willing to spend in terms of saving an Indian life, you come up with numbers going through the same set of computations using our Delhi Schedule of Rates from PWD in how much it costs to build a building. You come up with numbers that are absurdly low. And this is exactly what happens when you try to implement something without much thought. These numbers are actually not only in ISO 2394, they have not stopped in Europe, but they have given these numbers for all countries in the world. And I have just picked up numbers from what they propose for India. They did not do the computation, which is what I have done. And if you do this, you come up with numbers which are so low that you don't even need to engineer a building in India anymore. It will just stand because the hazards are not certain to occur. I hope you understand what I'm trying to say here. So this is an unintended consequence of adopting a measure that clearly has not been given much thought, but has been proposed beyond its applicable domain. And if you look at all the studies that have been done by our colleagues in finding out what the target reliabilities are implied in ISO 800, ISO 456, they're the same as we find in British codes, Euro codes, American codes, Canadian codes. And suddenly in 2015, ISO tells us that, no, you can build buildings because you are willing to pay less to save a life, and you can make your buildings 100 times less safe. So with that, I would end this. Obviously, this is not going to be ever adopted in India, but this is something that can happen if an academic does things without much thought, the practicality, and if the National Standards Organization picks it up without much thought either. So thank you for listening, and I'll be happy to answer questions.
Thank you, Professor Vaidwalian. I think if any questions are there from the participants, they can ask now.
This is Manohar. Can I ask a question?
Yes. Hi. How are you?
Hi. Yeah. Yeah. A lot of food for thought. Very nice presentation. I just want a couple of general comments. What is your take on performance-based structural engineering, where many of the decisions on, quantifying uncertainties and safety requirements is left to the client or to the designer? So where does prescriptive codes and performance-based structural engineering stand vis-a-vis the kind of issues that you are mentioning?
I think it's in the right direction, because a design code cannot think of all possibilities. By definition, a design code is the minimum standard. It does not have to be the only thing that you satisfy. And if there are ways that the designer or the owner can make the system or the infrastructure better, then they should be given the complete freedom to do that without violating what is absolutely sacrosanct for the concerned society. So I'm sure they would include human life, they'd include environmental damage, they would include ecological imbalance. So if a performance design code can very clearly state that you can do whatever you want, but you cannot violate these constraints that we hold dear with only with very low probability or probability that we find acceptable, I think then that fits in quite nicely with concerns of an educated society, and one in which risks and consequences are properly discussed. And then engineers and owners who act responsibly and satisfy those demands and requirements in the best possible way to them, best interest to them. So I think that is the ideal case. I don't know if I answered your question to your satisfaction, but
yeah, okay. Just another point, Dr. Balaji, can I ask?
Please.
Yeah. No, this is a very well-known question. Just I thought I can raise it so that I can come to know about your views on that. When we calibrate codes against observed performance of existing stock of structures, the failures are always at system level, observed failures. But whereas code calibration work is at component failure level. So how that, two things are reconciled?
They are not reconciled. What codes have said, I could give examples, but I think it will take time. The codes have said that these are meant for components. We understand that it's the system which matters. The system will have more reserve strength, but don't worry about it. Take that as a bonus, but we are not going to quantify that. So codes have acknowledged that. Now, in terms of more modern approaches, as you know very well, people are talking about system factors, or a component design equation being modified by a factor which takes into account the implied or the required redundancy, and you can make a component less strong if you can show that there is sufficient redundancy in the system and so on. But in general, so far our design is kind of, there's a dichotomy. We are able to analyze components very well, but when the whole system is nearing failure, nonlinearities are becoming very important, material and geometric nonlinearities. More and more members are failing. So in that extreme limit of performance, we are not checking the system or the components. So we are designing components to be safe enough, or very safe, and then hoping that because of that, and we have built-in robustness, the system will be safe. More modern design codes are also asking to bring in robustness or redundancy in a more explicit manner, like removing one element or some group of elements and see that your building is still standing. But I think that's the next frontier that people are tackling.
Okay, thank you, Badir. Yeah.
I did not go to the next slide. Please allow me.
Yes, please. Please go ahead.
Because Professor Manohar is here, I couldn't resist the temptation. I have to acknowledge him as one of my mentors, and many students who are my teachers actually, who have helped me in this work. Professor Manohar knows a few of them. But yeah, all these things that I said, these are things I've learned from talking to my mentors and my students. Anyway.
Balaji Rao, I have one quick question.
Yeah, please go ahead, sir.
Professor Bhattacharya, it was a very good presentation. This is a very complicated topic on, capturing socio-economic factor into any design and all that. However, I was expecting one aspect. the uncertainty, like, if you give the median value or whatever central tendency, so if the uncertainty is beyond, you can say, comprehensible things, then probably it could be a problem. So are you already giving 95% bound, or is it something, how do we manage? Because point value is one thing, and then we are giving the uncertainty. Because my worry is the aging. Normally, with aging, you have to do retrofitting and things like that. So we would like to know what is the time frame where we should go for retrofit or refurbishment and all that. So that those kind of things I can. Thank you.
Okay, I think there are two parts of this question. One is the uncertainty. So yes, as long as our mathematics is able to handle probabilistic information, we can compute probability of failure. The problem is, and it's good that we acknowledge it, many times we look for something because there is light instead of look where we really need to look. So it is said that only 20% of structural failures happen because of systemic problems, like there was a very high overload, or there was some poor member strength. More than 80% or around 80% of failures occur because of things that cannot even be modeled, human error. So we already admit the fact that what we are doing here is trying to tackle what we can handle. Gross errors, gross human errors are really something that probably cannot be handled with this sort of mathematics. And Professor Manohar can also say that he has given a lot of thought on modeling uncertainty. So, modeling uncertainty is a major thing, which can have perhaps the most uncertainty among all the random quantities that we think of. And finding that, estimating that is a big challenge. So if we can do that, some of these numbers might change. The approach will not change because it's still systemic. It's still mathematically supported by all our theories. In terms of degradation and aging, there obviously how the aging processes are occurring, what the in situ conditions are subject to tremendous uncertainty. Whether we can bring it to the manageable mathematics, that is the question. If we can, then the mathematical tools we have. But how to bring that, whether it's based on expert opinion, or whether it's based on testing, or whether it's based on something entirely different, that would tell us how sensible our numbers are. But a lot of these things boil down to the accuracy or the reliability of our models. And if there is time, Professor Manohar may give his expert opinion about that. But these numbers that I mentioned, these are all targets. There are no bounds on this. I know we have seen bounds, but for example, where Professor Cornell, when he derived the SSE FEMA target reliabilities, but this does not include that sort of approach. So I don't know if there is time for Professor Manohar to make any comments.
Thank you.
Manohar?
No. I mean, it's okay. I mean, it requires some thought to react to these questions. So maybe we can have a discussion on some other forum.
Okay. Any other questions? Hello? If there are no other questions, I hope there are no other questions. If there are no other questions, on behalf of the organizers, I would like to thank Professor Baidurya Bhattacharya for giving us such an excellent presentation about a very difficult topic. I can tell you, this is a very difficult topic because we are looking at acceptability of the society to adopt the standards that have been mentioned. And now, as he said, the future codes of practice are going to be, I think, Professor Baiduria may also react on this. I think in future they are going to be resilience. The one is life safety, the other is now they are similarly on all those people, they are evolving codes resilience based. I think resilience is much more complex and many other factors, extraneous factors need to be considered in order to come out with the others with respect to resilience based. So I think with this, I would like to thank Professor Baiduria Bhattacharya for giving such a presentation, and also for all the discussers who came out with such excellent questions. Thank you very much, Professor Baiduria Bhattacharya.
Thank you very much. I really enjoyed, and this was a very educational experience for me also. Thank you.
Thank you, sir.
Madam, yes. Up to you, madam.
Yes. So now, after the first keynote talk, now we have technical paper presentations. So we have two technical parallel sessions, that is a technical session 9. So I request the authors of technical session 9 to please stay in the main room itself. And the authors in a technical session 10, so a breakout room is created. So I request you all to move to the breakout room. So for clarity, so in technical session 9, A06, abstract number A06, A33, A43 and A44. So please stay in the main room. I request Subrata ji and Balaji Rao sir to kindly take over in the main room. And in technical session 10, we will be having the papers A19, A36, A52, A53 and A03.
Okay. Professor Subrata is there. Hello.
Once again, sir.
Yeah. He is the chairman for this session, isn't it, madam?
Yes, sir. I'm not seeing his name actually in the participants list.
Dr. Sujata, I just closed all, I pressed a closed rooms. I hope I did not make a mistake.
Oh,
all breakout rooms will close in 41 seconds, I'm seeing.
Oh, okay. That doesn't matter, sir. I will open it. Yes, they are breaking out, but anyway, they are closing, but once they close, I will open once again, sir.
Okay, I'm so sorry about that.
It doesn't matter, sir. Doesn't matter.
May I leave the meeting now?
Balaji Rao, sir.
Yes, please. No, Professor Baiduria.
Yes, sir.
Professor Baiduria. Actually, Professor Subrata Chakrabarti is supposed to be chairing this session. That is immediate session.
Okay.
Yeah, so
hello?
Dr. Balaji Rao, I am here with this structure lab. Actually, I have by default my machine name is there in structure lab.
Okay. Sorry.
I can start my video.
Oh, sorry, sir. I couldn't.
No. I can put my video on.
Okay. Professor Baiduria, sorry. He has come, Professor.
No.
Has come. Thank you very much.
Hello, Subrata. How are you?
Okay, fine. Hello, Baidu Jatra. I only listened last 5 minutes of your lecture.
Okay. So now, Daniel, please take care in the main room. I'm moving to the parallel session.
Yes. Okay. Now I will introduce Professor Baiduria Professor Subrata Chakrabarti, who is the chairman of this particular session. Dr. Subrata Chakrabarti is currently a professor and former head of Civil Engineering Department at the Indian Institute of Engineering Science and Technology, Shibpur. He is a fellow of the Indian National Academy of Engineering. Professor Chakrabarti did his bachelor's in civil engineering from Bengal Engineering College, Shibpur, MTech and PhD from IIT Kharagpur. He was a postdoctoral researcher at the University of Cambridge, UK, and University of Arizona, USA, and Technical University Aachen, Germany. In general, Professor Chakrabarti's research interest lies in the field of computational mechanics under uncertainty, structural health monitoring, vibration control, composite mechanics, etc. She has published extensively in authored peer-reviewed journals, authored textbook, and book chapters. As an independent researcher, she has completed a number of research projects funded by various agencies and is also active in important industrial consultancy. While his inspiring teaching, coupled with his innate urge for intensive research, has already established him as a distinguished academician at the national level, several awards and laurels have come his way. The Humboldt Fellowship for Experienced Researchers, the V.H. Joshi Award for significant contributions in structural dynamics, the INAE Young Engineer Award, the Boycott Fellowship, and Young Faculty Research Award deserve special mention. I now request Professor Subrata Chakraborty to chair the session, please. Thank you.
Thank you, Professor Balaji Rao. Now I think we can start the presentation, right? We have 4 papers. I think it will be good after 10 minutes presentation if we take a quick 1 or 2 questions for 2-3 minutes. That will be helpful, I believe.
Okay.
Okay, it's okay.
Yes.
Okay, so then we can invite paper number A06, who is going to present. Dr. Anup or Dr. Rao, you will present. So,
Dr. Anup.
Okay, we can start with A06. Please limit with 10 minutes presentation. That will help us.
Dr. Anup.
Yeah, you can start.
Hello, Dr. Anu? Hello? Yeah, Dr. Anup, you have to unmute. Dr. Anup, you have to unmute.
Yes, we can see the screen, but we are not getting your voice. Please unmute. Not getting his voice.
Am I audible now, sir?
Yes, sir. Yes, it's so fine. Okay.
We are not able to see the screen, Dr. Anup.
Yes, I'm sharing, sir. There's some problem with the audio.
Okay.
Sorry, sir. I'll just...
Hello, Anup, we are not able to hear you.
Hello, sir. Yes, sir. Now,
yes.
Sorry,
yes,
yeah. I'm sorry for the problem. So this is a paper on polygon-based model for performance assessment of pre-stressed concrete bridge girders, on taking into account only the pre-stress loss considerations. So this paper, as we know, that we have a lot of pre-stressed concrete bridge systems consisting of number of girders, and a time-dependent pre-stress loss in these girders due to creep and shrinkage as well as relaxation is a major problem that has been observed for the last 50-60 years, and which lead to large deflections and related stability, and even leading to collapse and safety issues. So there's a need to have periodic inspection and maintenance of these structures for ensuring the functionality and for extending the service life of these structures. For instance, if you see the MRTS system in Chennai, that is having large number of girders, about 270 girders of span 22.5 meters and 288 girders of 18 meter span, PSC girders, and which are almost exposed to similar type of girders, exposed to a similar exposure condition, that is the coastal anomaly in this case. So such a massive system, inspecting and maintaining such a massive system, all the girders going for inspection is not possible because of the limited funds available. So there's a need to have metrologies which can help us in assess the condition of this system, with system as a whole, based on monitoring or inspection of a limited number of girders. So there are already some methodologies are already proposed, like Markov chain model methods. So which requires, one of the drawbacks is that we need a inspection data on adjacent girders if we are using a Markov chain models, which may not be feasible always. So there have been other approaches like Polyand based model, which has been proposed, which is useful when we have even inspection data from randomly selected PSC girders. It need not be adjacent. That condition for Markov chain can be relaxed when you're using a Polyand model. And this procedure, what integrates is a Polyand model, which is a stochastic birth process model with the Priestess loss estimation method of ASTO and the assessment at different times in a selected number of girders. So the requirement of adjacency is relaxed here. In the present study, this methodology is combined with a performance-based approach using performability for determining the performance assessment of a BIT system. So in the present study, the proposed methodology is that one is the determination of allowable Priestess loss at different times. What is the allowable value of Priestess loss you can permit in your girders? That is determined based on ASTO LRFT code, detailed estimate using a ASTO LRFT. And this Priestess loss is considered the allowable Priestess loss because this is the values which you have considered in the design. And the estimation of actual Priestess loss using strain monitoring data on selected number of girders. Okay, then that is next step. And then estimation of condition state probabilities. Here we use the Polyand model to estimate the condition state probabilities of the BIT system based on information on limited number of girders. How to make an inference on the condition state of the entire BIT system is developed using the Polyand model, basic Polyand model methodology. And once you get the condition state probabilities, how to compute the performability of the system. Now, what is a Polyand model? It's a type of pure birth process, as we already mentioned, and it represents a system containing objects of two types. Basically, the basic Polyand model consists of a system having two types. It is you can consider an urn or a box, which has two types of balls. These objects are called balls. Normally, we call the objects based on their color, say white ball and black ball. In the present study, we are assuming that the balls are the PSC girders. What the PSC girders we are monitoring are the balls initially in the system. And the color of the ball indicate the state of Priestess loss. What is the type of the object is the color. So the ball color indicates the type of Priestess loss. So why we say that in the monitored girders, if suppose we monitor n girders, if B number of girders having Priestess loss less than the allowable value, then we say that these balls are black colored balls. We have this many black colored balls which are having Priestess loss less than the allowable Priestess loss. And white color indicate girders with the Priestess loss more than the allowable Priestess loss. So the initial configuration or the initial number of balls in the system represents the state of Priestess loss in the monitored girder. And in any basic step or the trial, we select one ball randomly from the ball. So this indicate equivalent to inspecting one more unmonted Priestess girder. So we select one ball and return to the urn with the additional ball of the same color. That is the basic step. Select one ball and return with the additional ball of the same color. So this is equivalent to inspecting one more monted PST girder. So what we are doing is that we are inferring the state of Priestess loss in each unmonted PST girder based on the color of the sample drawn. So the basic premise of the system is that more number of monted girders having Priestess loss more than the allowable Priestess loss indicate that there are more chances that the next girder to be inspected will have Priestess loss more than the allowable Priestess loss. This is the reasoning built in the Polyand model through the self-reinforcing property. That is, the observed ball color is more likely to be observed again. So this is the mathematical formulation, which I will not go to detail. But the final thing is that using such a formulation, we can get the probability distribution of percentage of girders in the BIT system having Priestess loss more than the allowed Priestess loss can be obtained for the entire BIT system based on a information from the limited number of girders or the monitoring of limited number of girders. How we can get the probability distribution of percentage of girders in the BIT system having Priestess loss more than the allowed Priestess loss. And once we get the probability distribution, we can also determine the condition state probabilities for the BIT system. So we have defined 5 condition states. That is very good. That means that 0 to 20% of the girders in the entire BIT system having Priestess loss. Only 0 to 20% of the girders having Priestess loss more than the allowable. Then satisfactory state, poor state, serious state, and critical state were almost 80 to 100% of the girders having Priestess loss more than the allowable Priestess. So once we get the probability distribution using Poilian model, we can also determine the condition state probabilities. Now, once we get the condition state probability, we determine the performance of this system using a performability model. So this is nothing but a stochastic reward model where we have a stochastic process which describes the evolution of the system, and a reward structure, which is nothing but a set of reward associated with the states of the system. And now this system is in a one condition state, we provide a reward to the system. So this is the model performability model. Suppose CS1 is the condition state, CS is the condition state, and probability of there being that condition state is given by P. Then R is the reward for that condition state. Then the expected instantaneous reward at any time is given by summation of Ri into Pi that time. So in the present study, the reward rate considered is like this. Very good means 10, because normally in both systems, whatever inspection or we are going for inspection or condition assessment, we rate it in a scale of 0 to 9 or a 0 to 10. That is the scale that we used. So considering that scale, we used a reward rate scale from 10 to 0 here. So I'll explain with an example. So we considered a bus system having 100 nominally PSC girders. So the girder details are taken from the literature. This is typically a type C girder with the specific details given as here with a span of 17.22 meter. And it is assumed that we are monitoring or inspecting 20 girders out of this 100. All 20 girders are inspected at the girders or monitored at the for these trains at the end of 10 years. We are monitoring at the end of. So initial configuration you earn as only 20 balls. Okay. So this is the allowable piston loss for the girder. Considered what is the allowable piston loss predicted using AASHTO is given here. We can see the different types of losses: relaxation, shrinkage, creep, and the total loss. And these values are considered as the allowable piston loss. Since these values would have considered in the design, we are considering them as the allowable piston loss. And using the Poilian model, suppose when we inspect the 20 girders, suppose it is seen that 19 girders are having piston loss less than the allowable value, and only one girder is more than the allowable value, which is shown by the first curve here. That is the initial condition. So this is the probability distribution at the end of 10 years. How many percentage of girders in the bus system will have piston loss more than the allowable value is given by here. So as for different initial configuration, what may be the initial configuration? For that, what will be the probability distribution is shown here. For we have shown for the 5 different values of initial configuration. For a typical initial configuration, we have seen here. Now, based on that probabilities, we can also determine the variation in condition state probabilities for different initial configuration. This shows the condition state probabilities for different initial state configuration. Each value of W represents a typical initial configuration. Means W1 means W0 means no girder is having allowable piston loss more than having piston loss more than the allowable piston loss. Coming to W20, all the girders having piston loss more than the allowable piston loss. So each of the W value represents the typical initial configuration, and gives the condition state probabilities at the end of 10 years. Now using these values, we can determine the performability. So this is the performability, how it changes for different configurations. We can see that how the performability is changing. So this is at the end of 10 years. So similar operation can be carried out for different years based on the initial configuration. We can get the performance variation with the time. So this will be useful in determining the performance of the system using limited monitoring data. To summarize, we have proposed a Poilian-based methodology for performance-based assessment. This is a data-driven approach with statistical learning, which can be used for structural monitoring. And it uses data from Monte Carlo train in a very limited number of girders. Useful when the monitoring data is from randomly selected numbers. It need not be that girders are adjacent to each other. The assumption is that all the girders are nominally similar and are exposed to nominally similar environment. And number of girders in the system is much more than the number of monitored girders for application of the Poilian model. And this reward rates, what we considered right now, is considered to be time invariant. But as such, in the practical cases, we can consider time varying reward rate, because when you go for higher periods of time, say at the age of 50 years or 100 years, we can reduce the rewards associated with the system. And also we can link the computer performability with the expert decision making. When we are giving the performability measure for expert to make a decision, there will be some uncertainty associated with the human mental process in making judgment. Theories such as Brunskian theory can be used for linking the performability measure with the expert decision making. Thank you.
Thank you, Dr. Anup. Now, floor is open for clarification or questions. If anybody has a question, we can take a quick 1 or 2 questions, please. The question? Oh, I think there is no question. So, I have just one query, Dr. Anup.
Yes,
Hello,
sir.
can you hear me?
Yes, sir. Please tell me, sir.
Actually, your model is applicable, say, for a particular stretch of a road where the gradars are there along a particular highway line. That means what I try to mean that this your all the gradar samples are homogeneous sample, right?
Yes, sir. True, sir. Yes, sir.
Okay, if I want to apply this for a particular region, that they may not be that construction time could be little bit different, or organization who has constructed could be little bit different, or say 2-3 roads in a particular region, say one sub-region, we want to apply this principle. How that can be possible?
Yes, sir. Right now, that is, we are not considered that. As we can see, we are only talking of the very large bridge system, which is having only similar girders. Means girders with the similar properties exposed to a similar exposure condition. That only we are considered here, sir.
So that means all those girders are constructed within a 1 or 1.5 year project period. And those things we are considering.
Yes, sir.
The way you are considering for this, your mass rapid transit system in Chennai. And
Yes,
there's
sir.
a particular link, right?
Yes,
for
sir.
those
That's
things.
the
But
scope
yeah,
of
it
this
will be really
model.
helpful for us. Say we are now working on all the bridge in and around Calcutta. We have to assess all these twisted girder bridge. But those are not homogeneous in nature.
Yes, sir. Yes, sir.
Some are constructed 10 years back, some are 30 years back, even some are 50 years back. So we are thinking whether we could use this type of approach. Okay, thank you.
Yeah, but can I answer that question, please?
Yes, yes.
Dr. Anup?
Yes, sir. Surely, sir. Yes, sir.
Yeah. Actually, Professor Subrata, actually, we have considered only 2 types of balls in this case, black and white, representing 2 limit states. But actually, Boolean model is such a general model that we can have multiple colors also, each color representing different states of the system, states of the girders. Thereby, it will help. What we have demonstrated is very simple and very fun, basic level. But Boolean model is very flexible model. Self-reinforcing schemes are there, and it can be used.
That's right. I understand.
Yeah. Thank you.
Okay. Thank you. Thank you, Dr. Ono. Now we have our next paper is A33. I think G. Srinath. G. Srinath. Srinath is present, I think. He is in the meeting. I think he is not in the meeting. Hello. A33. I think G. Srinath is not in the meeting. I'm not getting him here. What we should do? We should call the next one. Dr. Rao. Hello, Dr. Rao. Can you hear me? Okay. Nobody. Hello, Dr. Rao, can you hear me?
Yes, please.
The next speaker is not in the meeting room. Can you check it? It's G. Srinath.
Okay.
Analytical study on asymmetric building in comparison with regular building. But I'm not getting in the meeting room. Maybe he's not in the meeting room.
So yeah, let us not worry about that. But let us go to the next.
So we can go to the next one.
Yes, please.
We are going to the next one. So if he comes later on, then we can take up.
Yeah.
Next is A43, probabilistic global seismic damage analysis based on a novel factor mapping method by Vivas Paul and Professor Manohar. I think Vivas Paul is there. Okay.
Yes, sir. So I'm sharing that screen.
Okay, yeah, please start.
Just 1 second.
Put your video on for a couple of minutes.
Yes, sir. Yes, sure.
So that we can see you. Right.
Yes. Is my screen is visible there?
No, it's not coming till now.
Hello, sir.
Yes, now, yeah, we can see you. Now you share your, you introduce and you share your file, right?
Yeah, I have shared my screen. Is it visible there?
Yes. No,
Okay.
you are visible only, but your files are not shared, I believe.
Okay, let me check.
Check it and you do, and you just introduce you by 1 or 2 sentences, then you start your lecture presentation.
I think. Sir, can I present after the next? There is some problem in the formatting actually. So
It's a PPT file.
And, yes, sir. Actually, PPT file, but there is no power in my place. So actually, I am presenting from my phone.
Mobile.
So that is making some trouble. So,
okay, then. Okay, thank you. Let me check the next one. Okay.
Okay.
So I think we will resume a little bit later. So let us go to A44. This is subset simulation incorporating replica exchange algorithm for structural reliability estimator.
Yes,
I think I got Advaita or someone in the I see here.
Yeah.
Advaita Sharma is present now, so you are going to present.
So
you please just for a minute you put on your video and introduce yourself. Just take 1 minute for that. Then you start your presentation.
Okay, just give me a second.
Okay.
Okay. So can you see my screen?
Yes.
Okay.
Yeah.
Let me. Okay. Hello, everyone. I'm Advait Sharma. I'm a PhD student in the Department of Civil Engineering, Indian Institute of Science, and I'm working with Professor C.S. Manohar. Today, the topic of my talk is on subset simulation incorporating replica exchange algorithm for structural reliability estimation. And the talk is organized as follows. I'll give a brief background to my research, followed by my problem statement, analysis, some numerical illustration, and some concluding remarks. So my research is on the topic of computational reliability modeling. More specifically, I'm interested in developing algorithms to estimate time invariant reliability of structures. And my focus is on Monte Carlo-based estimation of reliability. Now, as is well known, in Monte Carlo-based approaches of estimating reliability, integration of variance reduction techniques becomes absolutely important. In the literature, there are many algorithms and techniques that have been extensively developed pertaining to variance reduction techniques for the past few decades now, but still some computational issues remain, which I will talk about in a bit. But before that, I want to mention that the focus of the current study is on variance reduction through subset simulation method. And so the idea here is to write the small failure probability as a product of larger conditional probabilities through construction of subsets, as shown here. And estimating each of these conditional probabilities requires us to draw samples according to a standard normal distribution conditioned on irregular domains. And this is typically achieved in subset simulation type methods through Markov chain Monte Carlo methods. And so this slide shows a visual sort of guide of how subset simulation method works. We have initial samples, we construct the first subset, we use MCMC methods to generate more samples, then generate the second subset, and so on until we get to the actual failure region. Right? And so having said that, now we get to the heart of our research topic, which is in challenges in reliability estimation. Now, it can be shown that when there are geometric features in a reliability problem, such as existence of multiple failure regions contributing significantly to the failure probability, or presence of disconnected failure regions, or sharp changes in performance function values, especially near the failure region, then these features manifest themselves as challenges in all algorithms of reliability estimation, be it first order or second order reliability method, or important sampling based methods, or even subset simulation method. And these problems are worsened when performance functions are implicitly defined through computational codes, where we don't even know if these kinds of complications have arisen in the relevant space. So our research is on how these difficulties can be dealt with, particularly in subset simulation type methods. And additionally, when do these kinds of problems arise in the context of structural engineering? In other words, what kind of physics brings about these difficulties and these complications in structural engineering, which is a question that has not really been addressed in the current literature either. Now, specific to subset simulation type methods, these geometric difficulties manifest themselves as difficulties in MCMC sampling. That is to say, when these complications are present in the limit surfaces, the MCMC sampling becomes challenging in some sense. Now, in what sense? Let's take a look. So let's look at what happens when, so let's say F is an intermediate failure region, and we desire to sample from the standard normal distribution conditioned on this region. And let's say these red samples are the seeds that we've obtained from a previous subset in the subset simulation. And we use our the Metropolis within Gibbs algorithm, which is typically used in subset simulation algorithm. When we use that algorithm on these samples, then we see that the samples here, they miss out on this important failure region to the right here. And so these are not really representative samples of the required, of the desired PDF. And so the quality of these MCMC samples are bad. And therefore, our problem statement then is to develop an MCMC method which, in presence of these difficulties, enables the generated MCMC samples to detect important failure regions, which would otherwise not have been detected by traditional MCMC techniques. And in order to solve this, our idea has been to use what's called replica exchange MCMC algorithm, which was initially developed in 1986 in the physics literature in study of what are called spin glass models for very low temperatures. And it was developed as an MCMC tool later in 1991 in the statistics community. So here the idea is we want to simulate from this PDF here. So we introduce an additional PDF, which we're calling the Explorer PDF, and we generate samples from this PDF as well. And the idea then is to exchange samples. So for example, if we have a sample, let's say at this point, and we have a sample, let's say at this point, then with a certain probability such that the condition of detailed balance is satisfied, these samples are exchanged. And therefore, this clearly allows these samples to detect important failure regions, which would otherwise have remained undetected, right? So, and this is just an algorithmic way of saying what I just told you. This exchange step that I just described of exchanging this sample to here, this can be written more formally like this, but we don't need to read through all of this. This is just algorithmic steps that we can follow. And so here it's kind of a schematic of the fact that the samples from this Explorer PDF, in some sense, assist these samples to detect this other important, this other important failure region. And so we get samples that are much more representative of the actual PDF here. And okay, before that, so having described this MCMC algorithm, this algorithm is then embedded into a subset simulation type framework. The one that we have embedded in is called the Holmes Diaconis-Ross method, which is slightly different from the subset simulation framework in the sense that the subsets, the intermediate failure regions have to be defined beforehand, which is done using a pilot run using a smaller number of samples. Now, having said that, now let us look at some numerical examples containing these difficult performance functions in the sense that I've described earlier. And we compare the performance of the proposed algorithm with the existing algorithms existing in the current literature. So here we consider the performance function of this form in the standard normal space. And we've compared the proposed method with 3 other existing methods. And so I invite you to look at this picture here where the samples slowly propagate towards the failure region, but due to a sharp change in performance function value towards near the important failure region, these samples don't really detect this important failure region. Whereas for the proposed method, due to the embedded MCMC algorithm, this ends up detecting this important failure region, which in this numerical results is reflected as a low value of coefficient of variation, in other words, sampling variance of the estimator. So this coefficient of variation of the subset simulation method is very high, 3.67. And when we employ this MCMC algorithm, it reduces drastically. And the performance function calls also remains fairly reasonable. Now, the second example is a structural engineering example of a forced vibration of a 2-degree freedom system. The details are given here. The random variables are the stiffnesses, and performance function is defined this way. And here as well, for a typical subset simulation run, we see that these samples fail to detect an important failure region here, and it only ends up sampling from this region here. But the proposed algorithm, again, because of the embedded MCMC algorithm, it ends up detecting both of these important failure regions. And therefore, again, this is reflected in the low value of the coefficient of variation compared to the other existing methods. The third numerical example is that of a structure that is prone to snap-through buckling. And once again, the details are given here. The performance function is defined here. And once again, a typical run of a subset simulation fails in identifying this important failure region because of the inability of the MCMC samples to sample well from the required conditional PDFs. Whereas for the proposed method, this ends up detecting this important failure region. And here we see that in the subset simulation run very highly underestimates the failure probability, by an order of magnitude of over 5. And so the coefficient of variation is also very high. Whereas, looking at the direct Monte Carlo estimate, we see that our the result that we obtain is fairly accurate with an acceptable coefficient of variation. And finally, here we consider the problem of reliability computation when the performance function is defined implicitly through a finite element code, which is run on a commercial software, Abacus. And the reliability estimation code is interfaced with the finite element program for reliability computation. And we've considered a deep arch here prone to snap-through buckling. And it's a problem that has been borrowed from Abacus' handbook of example problems. And this arch was first studied by De Depo and Schmidt in 1975. And so the details are given here, and Right. So the point here is that among all the existing methods, the first two methods failed in detecting the important failure region. That's why it heavily underestimates the failure probability, whereas this method here overestimates the failure probability. And the result that we have obtained here is fairly well validated by the direct Monte Carlo curve that is given here. And so in conclusion, we've developed an MCMC algorithm based on a replica exchange strategy to improve quality of MCMC samples. And we've shown that these kinds of difficult geometry that I've just described can arise in structures that undergo either vibration or failures triggered by bifurcation buckling. And we've demonstrated the effectiveness of the proposed MCMC method in various structural engineering examples. And the possible future direction is to develop a strategy to incorporate to deal with these difficult performance functions even in higher dimensions. And that's the end of my talk, and I'm happy to answer any questions. Thank you.
Thank you, Adit. Now, floor is open for any question or clarification. Please, anybody have any question? We can take one or two quick questions. Ready? No question? Adit, for you, there is no question. I just asked one question for you. Not question, just I want to know. So what I understand that you are exchanging the sample point, right? And for that you need one probability density function, the right side.
Yes.
This one. So is there any basis to define a separate? That I am interested to know. How to do that?
That's a very good question. The question of how you would define this PDF in the first place. That's a very good question.
That is very interesting.
So the idea is the following. I didn't say it because of the time constraint, but the idea is quite simple. The idea is we scale down this limit state function. So I think this picture would be better. We scale down this limit state function so that the average distance of these seeds from the origin becomes equal to 1. So that the failure region actually becomes much larger than it is. And the brute force Monte Carlo samples then actually lie.
Somehow you are doing some scaling here.
Yeah, scaling and then the Monte Carlo samples.
Okay, got it.
Right. Yeah.
That's fine. So nice. So if there is no question, then we can go for next presentation.
Sure.
Thank you, Adit. It's nice presentation.
Thank you.
Yeah. Next, Vivas, you are ready now?
Yes, sir. Yeah.
Okay.
I'm sharing.
Yeah.
Is my screen visible there?
No, still not.
Hello?
No.
No.
You are not
It was visible for a few seconds and then it went off.
No.
Yeah, I have shared the screen.
We are not getting here.
Can you confirm now?
No, it's not coming. I will confirm. Once it comes, I will tell you.
Okay. Is this visible?
Oh, no, it's not visible.
So Manohar was mentioning that there is no power supply in the campus.
Yeah, there is some maintenance going on for last 8 hours. There is no power supply, and all our inverters also have now drained out. So I am also barely managing to connect.
Okay.
Because can you mail this file to Dr. Rao so that
Yes, sir. Sure, that I shall mail.
then somehow we can make some arrangement for sharing by someone else.
Okay, sir. Then.
Dr. Rao, that could be a possibility, no?
Yeah. And I request the student to send it to balaji@gmail.com.
So, you please share your mail in the chat box so that he can send it to you.
Okay, sir.
balaji@gmail.com.
Sir, I am trying once again. I have answered
Okay,
and shared.
right.
Can you please check whether it is?
No, but it's not coming because.
Not yet.
No, not yet.
Okay, sir. Then I shall mail this presentation.
Have we mailed? Mr. Vibhas? How big is the file? Hello? Professor Subrata?
Yes, sir. Yes.
Actually, I don't know. I have not yet got that.
And there's another guy. Can you check the G. Sinha whether he's going to present or not?
Pardon me, please.
Any news about this paper number A33?
A33, okay.
G. Sinha. You can check just once.
Srinath is not there, available in the audience.
Okay. Vivas, can you hear me? Hello, Vivas.
I think he has muted actually. He has muted his.
He is muted now, yes.
There is a problem there, it seems.
Yeah, they have a power problem, no? They told me.
So, because they are trying to maintain. Can he come on the mobile and then try to connect? I don't know.
Think he is already on mobile. That is why he is having problem. So
okay,
he will be manipulating something now. So
okay.
Bibas, you can also send the file to me if you are able to hear.
Okay, that will be nice. How can we help this boy? Professor Manohar, he has to respond, you know.
Sir, I think Bibas and Professor Manohar are talking on call.
Okay, Professor Mr. Thank you.
Sorry, Chairman, I am trying to get the file from him, and my laptop still has power, so I should be able to run. He is trying to manage on his laptop, on his cell phone. So it's not easy to make that.
Okay, yeah, true.
Yes, Bibas. To Gmail or where yours? It has come now. Let me open. Yeah, just be there. Balaji.
So Manohar, please tell me.
See, I have the file, but I don't. Can I share the? I think I don't have the privilege to share right now.
No, you can. Yeah, you can just log in.
No, I am trying to share screen. Okay, let me see. Okay.
Yes.
Is it coming?
Yes, it's coming. It's coming.
Yes.
Yeah, Professor, there. It's perfect.
So, Bibas, are you there? You unmute and be ready.
Yes, sir. Yeah, I am here.
So
now I can.
You tell me when to move to the next slide. I will move.
Yes, sir. Yeah. So yeah, this was the trouble. Okay. Thank you, sir. Thank you, everyone, for having the patience. I'm myself Bibas Pal, a PhD scholar in the Department of Civil Engineering, IISc Bangalore, and this is my presentation on probabilistic global seismic damage analysis based on a novel factor mapping approach. And these are the outlines. Sir, please confirm that my voice is okay here.
Yeah, it's okay.
Okay, fine, sir. Perfect. Now, coming to the next slide, sir, please go to the next slide. Okay. So, seismic damage analysis is an important module in the framework of performance earthquake engineering. It helps the structural engineers to understand the possible damage state of the structure when the structure experiences an anticipating when the structure is subjected to an anticipating earthquakes. Now, in the literature, in this present study, I have taken two widely accepted is modified Parkin damage index, and the advantage of using that modified Parkin damage index is that it can be calibrated in a scale of 0 to 1. 0 signifies that there is no damage, 1 signifies that the structure completely damaged, and any value between 0 to 1 signifies different level of damage states, as I have shown here. Now, coming to the second, next slide, slide number 3. Yes, sir. Okay, this is the still moment registering frame that we have studied, and to perform seismic damage analysis, we have to perform a nonlinear time history analysis. To do so, we have modeled this frame in an OpenSys platform. We have used concentrated plasticity approach. That means we have assigned zero length nonlinear string at the possible location of plastifications. And on the rightmost figure, you can see the moment rotation characteristics or backbone curve of the plastic hinges that we adopted from the model of IMK model, or that is in literature widely popular as Krenkler model. Now, each plastic hinge is characterized by 8 modeling parameters, as I have mentioned below of this backbone curve. So in this problem, we have 56 hinges. So altogether, we have 448 number of parameters. Now, in seismic damage analysis, the major sources of uncertainty is uncertainty in input excitation and uncertainty in model parameters. In this particular study, we have focused on the uncertainty of model parameters. So we have in our problem, we have 448 number of random variables. So we have treated all these parameters as okay. Now coming to the next slide. Okay, here in this table, we have shown the probability distribution models and associated parameters, model parameters for a typical column hinge. And on the right hand side, we have shown the a few real sample realization of the backbone curve for that column hinge, along with the mean backbone curve that we obtained from Monte Carlo simulation. Now coming to the next slide. Okay, yeah, we should mention the scope of this study. As we already have said that we are not considering the uncertainty in input excitation in this present problem. So we have selected the input excitation from a set of 44 recorded ground motion based on incremental dynamic analysis. The bottom figures are basically incremental dynamics analysis curve or IDA curve for the 2 damage measures. If you see on the right hand side figure, you can or any figure on the right hand side figure, you can see that this black solid line that represents the north ridge excitation, that IDA curve closely follows the median IDA curve. So for our study, we have selected north ridge excitation, and we have set the intensity measure at 0.5 G so that the induced damage in the structure remains within the repairable damage state. That means the Park-Hendon damage index will vary from 0.2 to 0.4. Now here is the result of the probabilistic seismic damage analysis. We have plotted the PDF of the 2 damage measures. If you see on the right hand side figure, you can see that you can notice that modified Park-Hendon damage measure mostly varies between the range of 0.25 to 0.4, which is our goal objective. That is, it should be within the repairable damage state. Now coming to the next slide. Yeah. Now, so far we have performed probabilistic seismic damage analysis. Next level of analysis is global response sensitivity analysis. Now, why global response sensitivity analysis is important for a structural engineer? Structural engineers are often interested in knowing out of a large set of uncertain model parameters, which parameters or group of parameters are most influential in producing the variability in response in a predefined range. So there are a number of methods available for our analysis based on simplicity and computational efficiency. We have adopted factor mapping method, and further we have generalized that method. So in the next slide, okay, I will briefly explain the naive version of this factor mapping method. Then we will propose our generalization. So in factor mapping method, here theta is the input random variables, f is the performance function, and d is the response. The response quantity, the realization of the response is basically classified into 2 categories. That is realizations that falls within the range of interest, that is the set A, and the realizations that doesn't fall in the range of interest. In our problem, the range of interest is 0.2 to 0.4, which represents the repairable damage state for a Park-Hendon damage index. So accordingly, we classify the input realizations into two subsets or into two bins. That is theta given A that produces response in bin A. Whether the realization in theta given A complement produces the response in range A complement. Now, sir, please go back to that slide. Yeah. Now, for each random variables, using the realization of theta given A and theta given A complement, I can construct the that is cumulative density functions or probability distribution functions. Sorry, and we can get the maximum distance between these, which is nothing but Kolmogorov-Smirnov distance or case distance. The larger the distance is, higher will be the sensitivity of that random variable. So this is the naive version of this factor mapping method. Yeah, here we have generalized this factor mapping approach to incorporate the case of group random variables in global response sensitivity analysis. So here I will explain the proposed method using a factor map using some schematics. Here on the bottom left corner, these realizations, for the sake of discussion, we have considered a group of random variables which contains two components, theta 1 and theta 2. Now, this bottom left corner, these blue realizations are input realizations which produces response in set A. On the other hand, red samples produces response in A complement. So from there, I have constructed or estimated the density functions associated with these realizations, and we have measured the probabilistic distance between these two density functions. Now there are a number of probabilistic distance measures are available, among which we have chosen the Bhattacharya distance for this analysis. Now coming to the next slide. Okay, whatever I have said in my last presentation, here I have written here mathematically. So basically the Bhattacharya distance calculation involves the estimation of probability density function from its realizations. Now it becomes very difficult when the group size becomes large. That is, the number of the problems becomes high dimensional. So there we have explored three alternative methods to intelligently tackle this issue. Now here we have explored three methods, that is Nathap's transformation-based method, Kopula transformation-based method, and independent component analysis-based approach. Now coming to the next slide. Okay, here I will, these are the associated involved mathematics, but I will highlight the key features of these formulations associated with these three models. So consider a n-dimensional random vector U for which the realizations are available. Now the objective is to estimate the joint probability density function from its realization. So in Nathap and Kopula, you can easily see that I have highlighted the joint probability density function can be expressed as a product of its first order density functions of its components. Okay. So, and the dependence of the components is taken care of. For the case of Nathap, this Gaussian function, n-dimensional Gaussian function, that takes care of the dependence among its components. Okay, and for the Nathap, this is a generalization of the for the Kopula-based approach. It is for the generalization of the Nathap's method. Here, the dependence among the components are captured through a bit complicated expressions. I mean, if you have n-dimensional group or n-dimensional random vector, then you need nC2, that means n into n minus 1 by 2 number of Kopula functions to model this joint PDF. So implementation of this Kopula-based approach is a bit difficult when n becomes large. Another interesting approach is independent component model-based approach, where the realization of the original random vector U is transformed into another realizations of another random vector psi through independent component analysis. Now this, as the real psi component of psi is independent, so I can get the joint PDF of psi by taking the product of its first order PDFs of its components. Now now I know the relation between psi and u. These are related through a linear transformation. So using the rules of transformation of variables, I can get back the joint probability density function of u, the original random variables. Okay, so these are the three methods that we have used. Once I can estimate the joint density function, then it becomes calculating the vertex ray distance is just a simple step. Now I will apply those three methods in my frame problem that we have shown in some earlier slide. So this is the okay. Now coming back, just one second. Okay, now this is the frame. I have 56 hinges and each hinge has 8 random variables. We have grouped the 8 random variables pertaining to each hinges into 4 subgroups. The first subgroup basically describes the linear branch of this backbone curve. The second one traces the post-yield branch. Third one traces the softening and the residual plateau. And the fourth parameter that contains a single parameter lambda, fourth group, that basically controls the cyclic degradation. Now, here I have employed all the 3 methods that we have discussed: Nathap's-based method, Kapula-based method, and this ICA-based method on this 224 random variable problem. And particularly for Kapula-based approach, we have considered 2 copula. One is Gaussian copula, another one is T copula. And here we can see the peak of this, the distinguishable peaks that basically signifies the importance of this groups of the important groups. That basically designates the important groups here. So now we can see that all these 4 methods or 3 methods perform comparable. Okay, and in the next slide, okay, here I have superimposed all these 4 plots in a single plot, and I can see that peaks are captured in all these 3 approaches comparatively well. And now the question comes: which one modeler should use for performing global response sensitivity analysis? Now, to assess the relative their relative performance, I have compared this the performance of these 3 estimators based on 3 features. One is ease of implementation. Second one is the level of accuracy in modeling the dependence among the random variables in a group, and third one is the computation time. In all the cases, it has been found that ICA performed far superior than other 2 methods. Now coming to the next slide, we also achieved the model reduction. That means we have originally 448 random variables. So now what we did, based on our global response sensitivity analysis result, random variables, and treated only the top 70% random variables as the sources of uncertainty. And then again, we have performed the stochastic analysis. We can found that the CDF or cumulative distribution function of the damage measures matches each, actually matches. That means the uncertainty in the damage measure is not triggered or is not influenced by the bottom 30% random variables. Okay, based on their relative importance. So here I will quickly summarize our contribution. We have achieved stochastic model reduction. We have also compared the performance of the 3 estimators, and we suggested the best one from our point of view that we have observed so far. So far in this analysis, we have not considered uncertainty in input excitation, but that is one we will take in our future work. So coming to the next. This is one recent publication that we, in a structural safety paper, that here we have published the factor mapping method based on Nathap's approach, and the present conference paper is basically extension of this journal paper work. So you can also look into that for further details. And thank you, sir. Yeah, I'll be happy to have some questions and comments.
Sorry, I'm muted. Thank you, Bivas. It's a nice presentation, and also thank you, Professor Manohar, for your help, and that helps us to finally see the presentation.
Yeah,
So
it is my duty. I am a co-author, so.
Oh, yes. Oh, I see. You are a co-author. Right. That's right. So, if there is any question, please. No question? So, because I have just one small question.
Sure, sir.
Say, what I understand that you did some IM-based idea analysis also, no? Based on
yes.
that response analysis you did. But say the graph which you are showing, the index graph for different parameters, it is for a ground motion of a particular region or particular location?
It is for a particular ground motion.
Particular ground
particular
motion.
intensity
So,
measure.
my query is this. So if we change the ground motion nature, say instead of a far field motion, if it is a near field motion or spike like of, then is there any chances that this
yeah, sure, sir, sure. Yeah,
this outcome may change, get changed?
Yeah. Yes, sir. Sure, there will be change because of time constraint. I have not explained this. Yeah.
Oh, then
so
that means
if we change,
at this stage, these conclusions cannot be generic, right? It's a ground motion conditional on the ground motion. Is it something like that?
Yes, sir. Condition on the ground motion that we have selected. Yes, sir. Now it can.
Vivas, can I add something?
Yes, sir. Sure, sir.
No. This analysis can be integrated with hazard, and we can do it for a particular structure in a given region. Right now, it is for illustration only this. So a more general conclusion will emerge if we integrate this analysis with the hazard also.
For any other location, so procedure is generic in nature. It's basically the procedure of evaluating the index. Right now, for any other ground motion, you can apply the same procedure and see what is happening. What is the outcome? I think
we can
that way we can look into it. Yes.
No, we can consider an ensemble of ground motion and discuss the variability across that also.
Okay.
Right now we have not done
variation. Now, I'm not talking about statistical variation. I am
even even for a given region. That is why I said hazard for different sources, their associated probabilities, all that can be integrated.
Okay.
And
thank you, Vivas. So now,
yes, sir.
I think Dr. Rao, I think we have no other paper. So we have nice paper.
I don't see him. Srinath
I think he is not in the meeting room.
Yeah. So let us
maybe
now.
He is not present.
Perhaps this session can be.
So that now we can close this session. We have 3 interesting paper. This PSC Gardner paper, that is really a useful and practical work, and another one that subset simulation. He has on a very novel idea, which was from the physics in early 90s, but that idea really is good one for particularly for addressing that multiple failure region case, which is really a big challenge for structural engineering reliability community. And the last one, the Bivas presentation, this is seismic damage. It's also a very nice work, and I think it will be really useful in our building damage analysis. So with all this, and once again, I thank all the presenter and the authors of this paper. And now I think we can close the session. Or anything you want to say, Dr. Rao?
Yeah, please close the session.
Oh, I declared the session is closed. Thank you.
Yes, thank you. Thank you, Professor Subrata. It was a very nicely you have chaired. And now I think we have to go for the other keynote presentation, again given by Professor Subrata Chakraborty. I think from the
you
other
start
room,
now, or you have a 5 minutes?
I don't know. Just wait for 1 or 2 minutes. Because
okay.
From the other room, people have to come.
I will be in this meeting. I'm not leaving. Okay.
Yes, yes, please be here. We will.
Whenever you need, you just tell me. I'm
Thank
ready
you.
for presentation. Okay.
Thank you.
Okay. Okay. Thank you.
Hello, madam. Hello? Hello? Professor Subrata?
Yes, tell me.
Actually, can you kindly give us 5 minutes? Because
Yeah, that's fine, no problem.
it is running slow, late there. They will be joining.
Okay, that's fine, no problem.
Okay, sir. Thank you. Thank you so much.
6:30, I'm here, no problem.
Thank you. Thanks. Madam,
Yes, sir. Please start, sir. You can
can
start.
we start? Okay.
Kindly start, sir.
Yes, madam. Thank you, madam. Professor Subrata is there? Hello, Professor Subrata?
Yes, Dr. Rao. Yes, I'm.
And I think now we can start. I will just introduce.
Yeah.
Yes.
Just let me put it on.
Okay, I will now introduce. Okay, now the keynote speaker is Professor Subrata Chakrabarti. I had already introduced as a chairman. Now I want to introduce for all the audience. He is Dr. Professor Subrata Chakrabarti is currently a professor and former head of Civil Engineering Department at the Indian Institute of Engineering, Science and Technology, Shibpur. He is a fellow of the Indian National Academy of Engineering. Professor Chakrabarti did his bachelor's degree from Bengal Engineering College, MTech and PhD from IIT Kharagpur. He was a postdoctoral researcher at the University of Cambridge, UK, and University of Arizona, USA, and Technical University Aachen, Germany. In general, Professor Chakrabarti's research interest lies in the field of computational mechanics under uncertainty, structural health monitoring, vibration control, composite mechanics, etc. He has published extensively in peer-reviewed journals, authored textbooks, and book chapters. As an independent researcher, he has completed a number of research projects funded by various agencies and is also active in important industrial consultancy. While his inspiring teaching, coupled with his innate urge for intensive research, has already established him as a distinguished academician at the national level, several awards and laurels have come his way. The Humboldt Fellowship for Experienced Researcher, the V.H. Joshi Award for Significant Contributions in Structural Dynamics, the INAE Young Engineer Award, the Boy Scout Fellowship, and Young Faculty Research Award deserve special mention. He has several awards. What I have given is only a small segment of those awards, and he has published extensively in peer-reviewed journals. And I am sure you will get more about it when you see his Google Scholar site. His H-index is very high. Now, the title of his talk is going to be Adaptive Support Vector Regression-Based Meta Model for Reliability Analysis of Structure. Now, I request Professor Subrata Chakrabarti to deliver the keynote address, please.
Thank you, Professor Balaji Rao, for introducing me. I am really thankful to you and all the organizing committee members to give me this opportunity to interact with you. Bharti Sahab, I really miss you to meet you personally. But let us meet virtually. What can be done? Maybe we will meet very soon in some occasion. Thank you all. Now I can start my presentation. Hopefully I will complete by 30 minutes, that means by 6. Okay. I have a very brief presentation. So let me share it. Yeah. Share. My screen is visible now?
Yes, sir.
Okay. So my topic is adaptive support vector regression based meta model for reliability analysis of structure. Basically, what we will do here, we will present. Actually, it is one of my PhD students' work. So we have developed an adaptive scheme for meta model training, and that we have applied to support vector regression. So that is the basic work which we are going to present. So this is my outline of my presentation. Introduce the topic and then concept of adaptive design of experiment, and I'll give a detailed background of support vector regression because the work is for support vector regression applications. Then I will elaborate the algorithm and some. We have studied several examples. I have taken few selected examples from those studies, and I'll show some of our concluding observations, right? So concept of meta model, I think all who are working in the field of uncertainty are quite familiar with this concept of meta model. Still, let me just introduce in a single or one or two sentences that this concept of meta model is introduced as a fast running surrogate model, and it is basically a statistical explicit approximation of complex implicit phenomena, which otherwise need a lot of time to get the output response from a system, that we try to get it in an explicit manner and in a statistically significant way. That means we try to develop the model in such a way that it gives us the error within certain bounds, right? And that is basically the concept of meta model nowadays is a much more general way. They are calling it the machine learning. So basically the same concept lies with the meta modeling also. This meta modeling term was coined long back, whereas the machine learning may be the very maybe last couple of years this term is becoming popular. And the necessity, particularly in structural engineering, why we are looking for meta modeling or machine learning technique, because we know that both implicit and explicit reliability analysis method we need repetitive evaluation. If you go for a Monte Carlo simulation, you have to evaluate the performance function repeatedly to get the probability of failure. Now, if probability of failure is very small, then you may need a few thousands of repetition, maybe 1 lakh or like that. So we understand that what is the involvement of computation. And even if you go for a approximate methods like first order or second order reliability method, you need to calculate the derivative of the limit state equation, which needs a lot of involvement, right? So, and this becomes a formidable task, particularly when a finite element model is involved for performance function evaluation each time, because this will take enormously large computational time. Think about a typical civil engineering structure. You have a 10-story building, and one run of that building is take about 10-15 minutes. Now, if you have to repeat it for say even 10,000 times, so you can understand the involvement. So that restricts us the real-life reliability analysis problem with the direct and approach of Monte Carlo simulation or even the second moment-based approach. And here is the need of, or we are looking for an efficient computational scheme with a limited computational cost, and that is the relevancy of meta modeling technique in structural reliability analysis, right? And if you look to the various meta modeling techniques, I may have missed many more, but I have given some of the important meta modeling technique. And if you look to this first group, these are basically empirical risk minimization principle based meta modeling technique. The oldest one is the response surface method. Then you have ANN, radial basis function, PC, Kriging, most important one, Kriging, very popular nowadays, Mars, and many more such type of. But all these classes are under the empirical risk minimization technique. These meta modeling approaches are powerful, and it has been extensively used in the field of structural reliability in the framework of Monte Carlo simulation approach. But there is a key issue with this empirical risk minimization based meta modeling technique. That is, their accuracy largely depend on the number of training data. More the data you take, better your approximation is. And also, it sometimes taking more data is not the only solution for your problem. It sometimes leads to overfitting of the problem. So these are the two issues. Or sometimes we call it, these are the conflicting issues. If you take more data, you will get a better solution. And if you take a more data, you may invite or overfitting problem. So this is the difficulty with this traditional empirical risk minimization based technique. And there are another class of technique. Those are mainly the support vector machine is a different class. Support vector classifier, support vector regression, and subsequent development in the Bayesian framework of support vector machine, that is the relevancy vector machine. And if you look to this approach, these approaches are based on structural risk minimization. We will come to this structural risk minimization a little bit later on my slides. But generally, it is seen that the support vector machine, based on the principle of structural risk minimization, has better performance due to its inherent capability to circumvent overfitting problem. That is the conflicting issue in the usual empirical risk minimization problem. That problem is well tackled in structural risk minimization approach. As a consequence, improved response approximation ability it has using small sample learning. So this is the benefit or advantage of support vector machine over the usual metamodeling technique, which are based on empirical risk minimization. Right. So our today's discussion is mainly on the support vector regression. Now I'll come to the concept of adaptive design of experiment. What is that? So all we know that accuracy of reliability analysis is predominantly depends on the accuracy of the predicting of sign of the limit state function. Because we know if G function is greater than 0 or less than 0, whether it is a positive or a negative, that decides it. Whether its positive value is 1000 or 0.01, I do not bother. If it is 0.01 or it is 1000, if it is positive, I am safe. If it is negative, whether it is a -1 or -20 or -1000, we do not bother. Minus, oh, it's a failure. Okay. So we are interested in only the prediction of the sign, not its absolute value. And thus, there is a attempt to improve the performance of metamodel near the failure boundary. That means we are really interested in the value of the performance functions which is in and around 0, either in a positive side or in a negative side. In and around 0 means in the certain range, say maybe plus minus 0.5 or 0.25 plus or minus side. Those value outcome of the performance functions are most important to us. That is called that means the structural reliability community is interested on the approximation of the function near the failure boundary, right? So this is what is the observation in structural reliability. So to this end, including more data points near the limit state to construct the design of experiment will be naturally our interest, because if the approximation in and around the limit state function is important, so you use more data points near the failure boundary, and the far away from the boundary, you can take less number of data, because where at that region you are doing mistake in approximating the function or not, that will really not affect your reliability. So that is the basic concept of using the adaptive design of experiment. So you do a design of experiment in such a way that you can ensure more number of data points in and around the failure boundary, at the same time satisfy some basic principle of model fitting. Right. So for implicit limit state function, no, but the difficult, where is the difficulty? How you know which region is in and around failure boundary? Because the performance function itself is not an explicit function, it is an implicit function. So informations are not available about the failure boundary. So only option is you have to make a trial and error. That means you have to go through a iterative procedure. So this difficulty is addressed by the concept of adaptive design of experiment, basically some iterative procedure. And there are two philosophy or two way of doing this. Reconstructing an initial, so you start with the initial design of experiment with a coarser number of grid and get some approximation, then you refine in the next cycle, refine in the next cycle. So after a few cycles, you will get a good training data point to construct your meta model. This is the early work with Bouchard and Burgam in 1990 with the structural reliability. There are a lot of work where the entire design of experiment is updated in each direction. And there is another way which is nowadays becoming much more attractive. Our work is also on the second way, enriching an initial design of experiment by adding new data points iterative. That means we start with the initial design of experiment. Now we are not updating the entire design of experiment set. We are adding more data to the existing design of experiment. That these more data are such that those are close to the boundary and also satisfy some statistical condition. Right. So that is the idea of adaptive meta modeling. And if you see the application of this concept are enormous, and even these are applied to support vector regression based meta model also. Particularly if you see the apart from support vector regression in the Kriging approach, there are a number of literature, adaptive Kriging and MCS, AKMCS and its various invariants are available. You can see a large number of literature on the concept of adaptive support vector. Comparatively, in support vector regression, we could identify only 3 studies, but I must say that the adaptive concepts which are used in other meta modeling applications, those can be also suitably used in support vector regression approach also, right? But the our observation is that the sample size requirement is still an issue to achieve reasonable accuracy. And sometimes you may need almost 1,000 number of samples to get an acceptable accuracy in your estimated reliability, particularly when the reliability is in the range of 10 to the minus 4, minus 5 or minus 6. Then that's range. Sometimes you may need a number of sample about 1,000. And many of the adaptive sampling approach fail to estimate the reliability when the probability of failure is much less. So improving computational requirement and ensuring the desired accuracy for large complex system seems to be an important aspect that we have tried to address in our work. So specifically, we have proposed a 2-stage adaptive scheme to effectively obtain necessary training data to construct SVR-based meta model for Monte Carlo simulation-based structural reliability analysis. And as I already point out, the algorithm is hinged on the prediction accuracy of a meta model near the failure surface region. And in the first stage, a design of experiment is built by a space filling design over the entire physical domain. We call it the initial SVR model. Now, based on the prediction at the MCS points by the initial SVR, a subset of MCS samples are selected to enrich the existing design of experiment data by adding data point sequentially, right? And when we are adding the data point sequentially, we ensure 2 conditions. The magnitude of the limited function at the selected point is close to 0 or as close as possible to the 0 value. And the new point is dispersed as far as possible from the existing design of experiment. First one, to improve your accuracy. Second one, to avoid the clustering effect. So these 2 conditions is satisfied to decide the adaptive sample addition to the existing design of experiment. So before going to our scheme, let me give a quick view about the support vector machines. So support vector machine basically embeds the structural risk minimization principle, as I already mentioned. Now I practiced a little bit on this, and it found to be superior to the traditional empirical risk minimization principle. And basically, it minimizes an upper bound on the dimension space, as opposed to empirical risk minimization that minimize the error of the training data. So in empirical risk minimization, we basically minimize the error norm, and we typically use least square method or something to fit the data to a model. Here we do little bit more. Apart from this risk minimization, we make it structural risk minimization. That means we try to generalize the fitting problem. So it is this difference that equip SVM with a greater ability. That means here that means the minimizing an upper bound on the dimension space. When the structural minimization, that makes it superior, particularly with respect to what fitting as well as prediction with less number of data points. And that is eventually the goal of any statistical learning, any machine learning technique. That is our primary goal, right? So the SVM is typically used to describe classification with support vector methods. So let me explain it graphically. So this is basically the support vector. So say it's first, let us look. Initially it was developed as a classification problem. What is that? So you have 2 class of data. Just for explanation purpose, I have shown here. Say this is one class and this is another class. Now I want a straight line. For a 2-dimensional case, I want a straight line which will divide this data into 2 halves. You see, there could be infinite number of straight lines that can divide the data. Right. Now, out of this, that is the structural risk management. Out of that, you understand that there is only one straight line which will divide the data at the same time. It has the largest distance from the one class of data and another class of data. That means the distance between these 2 data classes is the maximum. So that line is our regression line. We will the classifier plane in case of a multidimensional problem. So that is what is done in basically support vector machine. We look for a line in case of 2 dimension, the line which divides the data at the same time, divide in such a way that the distance is minimum from the closest data to this line. So that is the basic concept of support vector machines. And if you put it in a mathematical setup, so if we have a data set, training data sets like this, L number of data set, X belongs to a space Rn and Y belongs to +1 or -1, that to represent two different class. Then we are looking for a hyperplane like this, which will divide this data either in a +1 class or in a -1 class. And the mathematical problem comes like this. So this is the line, and this is the minimum distance from the nearest data, and this is the distance from the nearest data. So what we try by in support vector machine classification approach, we try to maximize this margin. So the maximizing this margin is the generalization of the problem. So we try to maximize this margin, and mathematically it leads to a quadratic programming problem. That means maximizing this means minimizing this one. So minimizing this subjected to this condition. This condition take care about the classification of the data. So this is the basic problem, that solving a quadratic programming problem. Oh, I'm going in the back side. Now, support vector machine, where we only decide whether the data is in a one class or in the other class, but the function did not give you the numerical value. But in many applications, we are interested to know the numerical value of the function outcome. So this is regression. So support vector machine can be extended to regression for a set of training data. That means instead of getting a +1 or -1 outcome, you can get outcome anything between 0 to infinity or -infinity to +infinity. That is support vector regression. So the concept of support vector machine can be easily extended to support vector regression. The problem is that means you have to look for a set of functions that maps the regression, where A is a set of parameters and W is an unknown parameter that we need to determine. And for that, the regression function we have to find out such that it will minimize the risks, lowest expected risks, and at the same time, the function should be as flat as possible. That means your margin will be as much as possible, and at the same time, your expected risks will be lowest. So these two are typically satisfied by two mathematical concepts. This is a well-known concept. It is the basic same concept we use also in our empirical risk minimization based meta modeling approach also. So to minimize the risk, you have to minimize this functional, and to make it as flat as possible, that means you have to minimize the Euclidean norm. So these two conditions are simultaneously embedded in the typical support vector regression algorithm. So for a linear regression, the function is like this, where W is the weight vector and D is your bias. So error function is, this is the error, and that error you have to minimize. At the same time, you have to make W as minimum as possible, so it will be a flat error. And there are various error functions proposed in the literature. Depending on your problem class, you can pick up on particular type. But most common one, or the most popular one, is the epsilon insensitive loss function. And in our structural engineering application, this function is epsilon insensitive loss function is popularly used. That means, what is this? That means the tolerance is epsilon. That means if the error is within epsilon, we will neglect that error. If it is beyond epsilon, you have to make some correction, or you have to do something if it is beyond epsilon. As I told, that epsilon insensitive loss function is most popularly used. Now, what is this epsilon insensitive loss function concept? So we are assuming that the function can be approximate all the training samples within a tolerance of yi plus minus epsilon. That means you imagine about a tube of diameter 2 epsilon or a radius epsilon, within which if your data point fails, then we will neglect the error of that. Beyond that, error is considered, right, as a convex. So it can be formulated as a convex optimization problem. That means minimize the difference satisfying these two conditions. That means one in the left side and one in the right side about the hyperplane, and epsilon is your tolerance value. But this may not be true for all the training data points. That means if you want to be very rigid that all I will consider within epsilon, then this kind of hard constant may lead to overfitting. So to relax this hard constant, something is introduced in the SBR, that is, we introduce to slack variable, so that if some is away from the epsilon tube, still that can be considered within the database by introducing some slack variable, right? So if the data is even outside, that data is also accommodated in the formulation by introducing slack variables, and that leads to your optimization problem like this. That means we have put a penalty term for this slack variable, and finally this is your optimization problem. And this penalty term, you know that the C is the regularization constant and epsilon is the tolerance. So these are the two unknown constants you have to calibrate or you have to tune for successful application of SBR. There will be another parameter of course. Later on we'll see them. So finally, the optimization problem can be formulated in dual form with Lagrangian multiplier and applying the KKT condition. You will get the solution, that means the Lagrange multipliers, which are basically the support vector, and your functional approximation looks like this. Fx is like this, right? This is the dot product, and B is the bias, and alpha and alpha star are your support vectors, right? So this is what is linear support vector regression. Now you will find in many problems this linear boundary may not be sufficient to approximate your function, and you have to look for a high dimensional approximation. So let me explain the concept of nonlinear support vector regression. Now look to this data set. You see this data, you cannot divide this data with a linear classifier. But if we make a transformation of this data, instead of x1, x2, 2 coordinate system, you transfer it to a higher coordinate system, say higher space. That means if you make this transformation Z1, Z2, and Z3, then if you make another plot, then your data will look like this in the high dimensional space. Now you can see when you transfer this data to this high dimensional space, immediately you can see that there is a hyperplane is possible to classify your data in the two classes. So that is the basic concept of nonlinear support vector. So here key idea is you transfer your input vector x into a high dimensional space Z through a suitable transformation Z equal to pi x, so that the data which are not linearly separable in the original space, that could be separable in your transfer space. That's the basic concept. And later on you will see you really don't need to know exactly the form of pi. Some trick could be applied to avoid choice of a suitable functional form of pi. And just if you can remember from our previous slide, this is the regression equation in linear space. Now what we need to do, so xi and x, that has to be replaced by pi xi and pi x. That is the concept. So when you solve the problem in a high dimensional space, so x is replaced by pi x, and that means when you are replacing x by a pi x, that means you have to do a dot product. So explicit computation of dot product in high dimensional space will be time consuming, and it will be really a tough job in terms of computational involvement. So this is elevated smartly by introducing the concept of kernel function. Kernel function concept is used in various fields of mathematics, and here we can use the concept of kernel function to replace the dot product. And once you select a kernel function, then SBR computation will be just simply calculation of the kernel function. And there are various standard kernel functions available in the literature. Out of this in structural application, this Gaussian radial basis function is most popular, and this is the form of the kernel function where your sigma is another parameter. I have told that there is one parameter C and epsilon, then you have to introduce another third parameter sigma here, that is the kernel parameter, and these three parameters you have to tune accordingly. And once you introduce the kernel parameter, now you see the problem is almost like a linear regression, only phi xi phi x is replaced by kxi kxt. Then you solve the optimization problem, get your support vectors, and that leads to the approximation function. This is your approximation function. You see, procedure is identical to the linear regression, only in that case it was on the xi.x, now it is kxi.x. So you have to properly choose a Gaussian radial basis function. Otherwise, the procedure remains almost similar to the linear regression. Of course, there is one additional parameter c, sigma here. And if you look to its implementation algorithm, these are nowadays readily available in MATLAB platform, GAN toolbox. You can readily use for linear as well as nonlinear regression fitting with any kind of basis function. There are number of basis function available with the toolbox. And of course, as I told you that you have to go for a hyperparameter tuning, and hyperparameter tuning, we have used here leave one out cross validation approach. Basically, what is done? We calculate the generalized root mean square error by leave one out cross validation approach without any further increment of the sample size, and we minimize this GRMS value. For that, we have performed a grid search over C and epsilon to minimize the sigma value, that the Gaussian parameter, and make a proper selection of C, epsilon, and sigma. Actually, this work we have published here, and these details of this work you can find here in Probabilistic Engineering Mechanics journal. And this is the algorithm of this parameter tuning. That means one grid search over epsilon and another grid search over C to take the final decision about C, epsilon, and sigma. Now, our proposed two-stage adaptive model is like this. The first stage is, as I told, that first an initial design of experiment is built by a space filling design over the entire physical domain of the random variables. You can use the uniform UD table. Then the optimum choice for the initial SVR parameter C, epsilon, sigma is obtained by leave one out cross validation approach, as I mentioned in the previous slide. Then once you have constructed your initial SVR model, now you can get an approximate failure bound. It may not be a correct bound, but you will get some idea about the failure bound like this, right? So this is your red at the failure point, these are the green at the safe point, and you have some rough idea about the failure bound. So we start from here. We go for a second stage, that means you prepare a reduced space from where you have to pick up the data to add in the existing design of experiment. So what we did for this? First, you select n f/2 numbers of MCS points from the arranged list of ascending order of the magnitude of the approximated limits of function from unsafe. That means from the all red data point, you sequence it. Lowest one, lowest one, lowest one, lowest one, gradually increasing one. And first nf/2 point number of data you keep aside. Similarly, you keep another nf/2 number of point data from this green side. So nf/2 plus nf/2, total nf number of data points. These are your reduced space. That means these are the most vulnerable data points. Now, these data points we will try to add in our existing design of experiment. Right? That is the basic idea. Now, for each point of the reduced space, now which point to take first? For that, we have calculated the Euclidean scale distance of that. There are black are the existing data points, and these are the new nf number of candidate samples. Now we calculate the Euclidean distance. Now out of this, which one to select? The point of reduced space correspond to the maximum value of this minimum distance is selected, and this will ensure you the clustering, right? So you pick up the first point, then repeat the procedure, pick up the second point, and take sufficient number of data points to add in the existing red and green sample. Over that, these are the blues are the additional data points. Now, this is the addition of additional data point from the sample space. Now, approximately half of the size of the initial DOE points are usually added to build the second SVR. There is no fixed guideline. This we have intuitively assumed that if we have started with a 30 number of initial sample, we will make 15 number of additional sample, that blue sample, according to that two criteria, right? Now we construct a second SVR model, right? Now with this updated, that means we have initial design of experiment. We have added half of that from the adaptive sampling, from the reduced space. We get a initial number is N0 plus N0 by 2. Now with this additional data sample, you reconstruct the SBR model. Now with the updated SDR model, again you rebuild the reduced space. Exactly the similar procedure, the way we did for the initial SBR model. You rebuild the SBR model. Now based on the maximum criteria, now two more data points from the new reduced space is chosen to update the SBR model. Now once after formation of the second SBR model, we have updated the reduced space. Now from this updated reduced point, each time you take 2 data points, add to the existing design of experiment, construct the SBR, update the SBR, and this is an iterative procedure. So you add 2, 1, update the SBR, again update the reduced space, again add 2 points, continue this until convergency, and you take a suitable convergency criteria to stop the algorithm. We have taken the 5% between 2 subsequent iteration is taken as the stopping criteria. So this is what is the algorithm, and we have explained it through few examples. First one is a 29-dimensional standard test problem. This is the function which need to estimate approximate, though you really don't need meta model, but for explanation purpose we have taken. So this is the limit state equation, and these are the standard data for all x, and we have estimated the probability of failure with the initial SBR, that means the usual SDR, and by the proposed approach, and we have tried to compare it with the Monte Carlo simulation result. So you see this red one is what is the approximation of the reliability result by initial SBR, and as we update it after few iteration, we got this green, this blue one are the updated results, and black ones are of course the exact results or the direct Monte Carlo simulation results, right? So we can easily realize the improvement. And also we have compared with various other standard meta models which are also used for reliability calculation to compare with, and I think this curve is a little bit clumsy, so you can better realize it from this error plot. So you see the error by various. So here in SBR we started with a 30 sample and it converts with a 49 sample, and you can see how the percentage of error in calculation is reducing. This is for the Kriging. It also needs 49 sample. RBM takes 53 sample. Here also it takes 49 sample to convert. Out of this, RBM works is not working very well, but you can see the SBR is consistent, and in most of the cases it is better compared to the other meta modeling approaches. Then we have taken another little bit realistic problem. You need to evaluate the performance function for finite element analysis. These are the data. It is a space dome truss. So limit state function is the central deflection to exceed certain values. These are the data. And this is again the similar kind of comparison. You can see improvement in the reliability. This is comparison with the other meta modeling approach. These are the error plots. Here also you can gauge that SBR is consistently better in almost most of the cases. And this is some parametric study. I have changed the load value, mean value of the load, coefficient variation of the load to see whether it works in the other scenario also. And we have made another interesting, that means you are using 49 data. Instead of doing the adaptive sample, if I start with initially with 49 data, then what will be the reliability, and whether when you are applying the adaptive sampling is really working or not. To check that, we did it with the single shot design, and you can see the error is as high as 10 to 15%, whether here the error is below 5%. So it shows that it's working. Though I have not shown here, we have tried the reliability analysis by this adaptive sample with various initial DOEs to understand the robustness of the approach, and we have seen even if you start with a different set of initial data, it converts to a almost similar kind of final estimate. Then finally, we have taken a very large problem, This is a 6-storied building, multi-storied building, and it has 16 columns, lift, case, foundation, the soil, everything is model. You see total 9,700 nodes. You have 882 brick elements, 384 beam elements, and almost 8,000 cell elements to entirely model the finite element. And of course, we have not modeled it. The details of the finite element model. Nowadays, a lot of things are available in GitHub, so you can find this model. It is the Abacus model, and all these model details. You can directly run it there. You will get this model in GitHub. We have taken the model from there. These are the 39 random variables of the building, and limit set function is the maximum von Mises stress developed in the model, and sigma 0 is the threshold value. So if it exceeds this value, then it is considered as failure. So accordingly, we have approximated the limit state equation, and this is the result. We have done some limited work because the time required for to run this program is abnormally high. So we have started with the initial meta model of 50 samples. Then iteration goes on like this: 50, 75, 77, 79, like this in different stages. 5th iteration, 6th iteration. Then for direct Monte Carlo simulation, we could not make a full MCS, just a limited MCS, and as if this is the correct result. Of course, it may not be the correct result, but it will get very close to the correct result. So 0.0236 is the benchmark result, and you see how SVR is merging towards this, and how the other methods, popular meta modeling approach, and you can see that this SVR based proposed adaptive approach works better than the other. RBM works least. Possibly this parameter tuning of RBM was not proper in our calculation. That could be the reason, but we have to check this part in more details. So with this, I believe I can conclude my work. So the effectiveness of a two-stage scheme to obtain training data to construct SVR-based meta model is presented here, and the scheme provides a much improved estimate of reliability compared to that obtained by the SVR model constructed with initial design of experiment data, and the SVR model by the proposed approach, and that obtained by a single shot design with the same number of data, so improved performance of the proposed approach. And the improved performance of the proposed SVR approach is noted for wide range of allowable limits and uncertainty in the random parameters. That means so its robustness, and also the effectiveness is noted for design of experiments starting from different initial sample size, confirming the robustness of the approach for desired local response approximation capability. That means our initial goal was we want to improve the approximation capability of the meta model in and around the Fourier sample. And from the numerical result, now we can draw the inference. Yes, we have achieved that target. But there is a bottleneck of this approach. If the initial SVR detects very small number of failure points, the algorithm cannot be applicable state forward. That means you are updating the model from the reduced space. Now in the reduced space, if NF number is very small, 1 or 2 only, or 3, then you cannot iterate. And when it can occur, when your probability is very small, then NF will be obviously very small. Then this is the bottleneck of the approach. Of course, we have further extended this work to avoid this bottleneck. Maybe that will present in some another occasion. So I want to specially thank my PhD student, Mr. Atin Rai. Actually, it is his work, and he is going to submit maybe by next week. And the work what I have presented, you can get more details of this work. We have already published this work. It is his PhD work. And the bottleneck also, that work also we have very recently published, where we have addressed this scarcity of sample issue, so that you can extend the approach to a very small probability of failure estimate. So with this, I'll conclude my work. Thank you. Thank you all. So now I'm ready to take questions from you, audience, please.
Can I just one comment?
Yes.
Professor Chakrabarti,
Yes.
it was a really very lucid presentation, and the kind of academics that you have brought in. I really compliment you and your team. You are able to hear me? Yeah.
Yes. Yes.
Yeah.
I
I really compliment it. Now, I have only one question. We in electronics reliability modeling, or we call prognostics and health management. That means you are trying to prognostize the degradation in the system, and then you try to predict the failure before the incipient of that fault. Now, there the problems are like this. Yes, all the support vector machine and all the intelligent tools and all that. One issue is catastrophic failure. So even if we collect more and more data points, the time available for management of those failures, or consequences, is in question. How much time is available with you? So even if I leave the catastrophic failure, to handle that problem for electronic cards, other methodology has been devised, and it is called canary-based approach. Again, there also you are dealing with structures, weld failure, solder joint failures. What are the symptoms that are available to you and all. But in canary failure, that you are calling it is a meta model. We call it as a physics of failure. So you go into the detail of here the physics is such that you design a component which can affect the reliability. Let's say microchip. I mean, most complex component, CMOS. Now you design a canary. That means the small component, miniature component of that equivalent main component, and then it is made to fail before that. I mean, you determine that reliability that it should fail before the main component fails. Okay, so there you capture this catastrophic failure and all that.
Yeah.
Now you are talking of mega structure. Probably you are in the domain of mega structure.
No, but that part is what you are saying, that small component will act as your safety valve. It's like that.
No, I'm not going to safety valve. I'm going to the electronic device. Yeah. So how you handle this catastrophic failure, or for that matter, where we are having physics of the component or mechanics of failure is not very clear. Leak before break. Let us say take that case, in the pipelines. So how you handle those scenarios, because they are very important for to
yes, I understand. Because for those cases, generating data is a very tough job.
Yeah.
Because you do not have the enough data, particularly this disaster kind of happenings. You cannot replicate the data, no? And for any kind of meta modeling and machine learning, the basic difficulty is you have to get enough number of data.
True.
And for this catastrophic, you really have how many? You have hardly 4, 5, 10 data, maybe not more than that. That's the problem.
Even if you do experiments and develop in the lab catastrophic failure, the variation will be so much,
No, in the lab, whatever you will develop, that will be much away from your actual scenario.
Exactly. That's what I'm saying. Because environmental factors are not there.
Yeah. Much away from that. That's the problem with this type of problem.
So thank you, but it was a very, very good presentation, Thank you so much for joining this NCRS. Yeah. Please. Over to Balaji Rao, sir.
Yeah, thank you, sir. I'm very happy to say that Professor Subrata Chakrabarti has presented he has made an excellent presentation about the use of support vector machines in determination of failure probability of the structures and structural components, which is it's a challenging problem. It's a challenging problem which he has solved, and he has compared the results of the failure probabilities obtained using support vector machine with those which are already in vogue, and then finds that this method is very, very efficient. I'm sure that it is going to be very useful for the others too. With this, on behalf of the organizers, if there are no other questions from the audience, Can we give 1 or 2 minutes for the audience to ask a question?
Absolutely.
Are there any questions to Professor Subrata Chakraborty? Now participants can ask queries or doubts or questions to Professor Subrata Chakraborty, who has made a keynote presentation. If there are no other questions, I would like to thank on behalf of the organizers, Professor Chakraborty, Subrata Chakraborty, for making such a lucid presentation. Thank you very much, please.
Thank you. Thank you, Dr. Rai and Professor Bhadde.
Yeah.
Very much.
Thank you so much.
See you
I need
sometime.
your phone number. I'll call you. I need
Okay,
your phone number. I'll write an email to you. Yeah. Thank you.
Okay.
Thank you.
Thank you.
Now over to Madam, Professor Sujata Madam.
Thank you, sir. Now we are in the final paper presentation session, that is technical session 11. So where papers whose abstract numbers are A16, A19, A22 and A40 will happen in technical session 1, so which will be in the main room. And I request the authors of A26, A41, A42 and A20 to kindly go to the breakout room, which is named as technical session 12.
Good evening, everyone.